In this video, we are going to talk about using vectors with trigonometry to solve this application problem. This is a really good problem of something you're going to see at the start of your Calc 3 class, introducing you to using this vector notation. So I'm just going to give you like a little hint of what is to come. And you really need to understand vectors before you can do multivariable and vector calculus, which is essentially what Calc 3 is. So here we have a 350-pound block. It is suspended by two cables. The blue one is R and the red one is S. And at point A, there are three forces acting. Okay, so we've got the weight of the block, we'll call that W, pulling directly down, and then again, cable R and cable S. So we'll call this guy R, and over here, S. And those guys are pulling upward and outward. So we want to find the tension or the poundage being applied to each cable. Okay, so this is a weight pulling down. We also have pounds in either of these directions. We're given a couple of angles here that are going to help us. One thing we want to remember is that when we are talking about angles and we're using this vector notation, we want to think about 0 degrees and a positive counterclockwise rotation to 360. So something to consider would be that this 37-degree angle, that is a 37-degree rotation. But 55 degrees, how would we measure that as a rotation? So that would be 180 minus 55, which gives us 125. 125 plus 55 sum to 180. So we're going to be needing to use that 150 angle measurement as well as a measurement all the way around to 350, or to that 350-pound weight pulling down. And so what we see is we have that 270-degree angle there. So I've drawn us another picture here to just kind of relate how we're going to change those angles when we use them to solve the problem. So when we think about the angle associated with 350 degrees, that will be 270. When we think about the angle associated with R, that will be 125, and the angle associated with S will be 37. Okay, so let's start talking about setting up this problem and how we would do that. The first thing we want to think about is that this is a balanced system in a sense. Everything is still and not moving. And when we think about something being in balance, then that means the vector sum, if I'm adding all of these vectors up, they should be equal to my zero vector. Or rather, vector W plus vector R plus vector S is equal to 0. Another way we could think about it would be setting it up like this, that the sum of R plus S is countering directly that weight, which is pulling down. So I'm using a negative here, or you think about moving that to the other side. Okay, but this is a balanced equation. So R plus S is equal to the opposite negative, that weight pulling down. In this situation, we're just going to use this vector sum that I have here. So the first thing we want to do is write each of these three vectors in our trig component vector form. So our trig component vector form, that says we're going to have the magnitude of the vector times cosine theta I plus sine theta j. This is a pattern that we'll use with that unit vector in the position of horizontal and having cosine attached to the horizontal unit vector, and then j, a vertical unit vector, attached to sine. So if I set up my vector for W, my weight, and we do know the magnitude of this weight, 350 pounds. So we have 350. I don't need the absolute value bars. And then we'll say cosine of the angle. So I've got cosine of 270 I plus sine of 270 J. I and J being those vectors telling us the direction. Now in this situation, since I know the cosine and sine values for 270, I can simplify and write my W vector as 350 cosine 270I, that would be 0I. Sine of 270 would be negative 1J. So we have our W vector here that we're going to need to use, but we also need the R and S vector. And when we think about the magnitude of the R and S vector, those are unknown, okay? So let's try and set this up. How would I write R? R is going to be the magnitude of that vector R, which is just R, and we'll say cosine of 125 I plus sine of 125 J. Now in this situation, these are not angles that we know on the unit circle, so I can't just directly simplify it. Now, I do know my R is going to be positive, so I'm not going to write these magnitude bars for the remainder of this problem. I'm just going to call this R. And I'll go ahead and distribute that. So I'll think about my R vector as being R cosine 125 I plus R sine of 125 J. And then of course we're going to do the same thing for our vector S here using the angle 37. So keep in mind, remember what we talked about at the beginning, how I'm choosing these angles. I'm taking them in a counterclockwise positive rotation oriented off that standard position 0 angle vector. So lastly then, vector S, that's the magnitude of S, and the angle associated with the S will have cosine 37I plus sine 37J. And again, we'll simplify that as well. So S equals S cosine 37I plus S sine 37J. So I have my three vector representations that I'm going to use to solve this problem. Now, also recall we said that W plus R plus S is going to equal 0. Or rather, we'll say W plus R plus S is equal 0I plus 0J. So I'm going to write that out. And what we see here is that I have W plus R plus S equals my 0 vector. Now, we want to solve for R and S. So the way we're going to do this is I'm going to look at my I components. I have two I's on the left and one I on the right, as well as my J components. I have three J terms on the left and one J term on the right. So I know that my I's are equal to 0 and my J's are equal to 0. Let's look at setting up this system of equations from what we're looking at here. Leaving out my J's and I's, I'll say R cosine 125 plus S cosine 37 equals 0. So that's where this first equation came from. Leaving out my J's, negative 350 plus R sine 125 plus S sine 37 equals 0. Here I can simplify that system and then we will solve. So essentially all I've done is take that negative 350, and actually when I move it over it should be positive 350. Now we can solve these systems using the substitution or the elimination method, Or if you understand matrices, you could put this into a matrix to solve for R and S and row reduce. Now that's not something you need to know how to do. It's just something that may shorten your calculations if you're familiar with that. Obviously, make sure that you are in degree mode if you're using your calculator to use the matrix. You won't get the correct answer if you are in radian mode. All right, but we're going to use the substitution method. So I'm going to isolate a variable, specifically r, in this top equation. So that's the same as r times cosine 125 equals negative s cosine 37. Or rather, I could divide by this cosine 125 on both sides, and I'll just have that r equals negative s cosine 37 over cosine 125. At this point, since I know this is equal to r, I'm going to use substitution to sub that in and solve the equation. At that point, I'll have the equation only in terms of s. I will only have an s variable. So this is negative s cosine 37 over cosine 125, and then that sine 125 will just end up in the numerator. We still have plus s times the sine of 37 equals 350. Factoring out an s, that leaves me with sine 37 minus cosine 37 sine 125 over cosine 125 equals 350, and then by division, we'll see that s is 350 divided by this entire expression, which is sine 37 minus cosine 37 times sine of 125 over cosine of 125. Now this is an expression I can plug into my calculator. I can get this value. I could have approximated that number up here and used the approximate number in my calculations, but of course I like to manipulate things and leave everything as accurate as I can when I'm working through these problems. Cleaning up my screen a little bit, plugging this into my calculator. You make sure you can evaluate this in your calculator properly, but you get the output for S is 200.87. We'll just say that S is roughly 201 pounds. So there's 201 pounds of tension in cable S. How are we going to find the tension in cable R? Well, if we know S, and again, use your exact value to plug it in, we can plug it right into that equation up there. That R is roughly 280 pounds of tension. And that should make sense that the tension on R is far greater than the tension on S, because coming back up to our diagram, most of the weight is under R. S is pulling more to the side, so it's not having to do as much work. So I hope that helps you understand. You might see something on this or like this, similar to this, on one of your labs, but you're not going to be tested on this. I just think it's very important to show it to you, especially my engineering students moving forward, because you're going to be doing a lot of manipulation with vectors like this when you get to Calc 3. As always, email me with any comments, questions, or concerns, but that's how we use the trig vector notation to solve some application problems.